Imagine for a moment that you are falling. The darkness in front of you isn't just an absence of light, it's an absolute perfect void, a place where space itself has been erased. Below you, or is it above, lies a point of impossible gravity, a monster that has already devoured the star that gave you life and the planet you called home. You are crossing the event horizon of a black hole. Here, the laws of reality are rewritten. The dimension you knew as space becomes a relentless one-way current of time, pulling you forward. And the dimension you knew as time becomes a place, a destination you are doomed to reach. The singularity. A point of infinite density where all the matter of a stolen star system is crushed into a volume smaller than a single atom. This is the ultimate end, the final silent scream of matter and energy being erased from existence. But what if this isn't an ending at all? What if this cosmic funeral pyre is actually a crucible of creation? What if the singularity at the heart of a black hole isn't a tombstone, but a seed? The seed of an entirely new universe, with its own stars, its own galaxies, and its own life, born from the death of another. This is the story of a theory so profound, so mind-bending, that it rewrites everything we thought we knew about our own existence. The idea that our entire universe, every star, every planet, and every person who has ever lived, might exist inside a black hole. Before we journey past the point of no return and unravel this extraordinary mystery, make sure to subscribe to our channel. That way, you won't miss the next chapter of our voyage into the deepest, most forbidden corners of the cosmos. Prepare yourselves. We are about to question the very nature of reality. Our story begins with two of the greatest paradoxes in all of science. The first lies at the heart of a black hole, where Albert Einstein's theory of general relativity predicts a singularity, a point where the density of matter becomes infinite and the laws of physics break down completely. It is a mathematical dead end, a place where our understanding of the universe simply ceases to function. The second paradox lies at the beginning of our own universe. 13.8 billion years ago, everything we can see, all the matter and energy that would eventually form hundreds of billions of galaxies, was compressed into a singularity of its own. From this single, infinitely dense point, the Big Bang erupted, creating space and time as it expanded. For decades, these two singularities were treated as separate, unrelated problems. One described the ultimate end of matter, a cosmic tomb. The other described the ultimate beginning of our reality, a cosmic womb. But what if they are two sides of the same coin? What if the crushing death inside a black hole in one universe is the explosive birth of another? This is the core of the black hole cosmology theory, a concept that suggests our universe was born from the collapse of a star in a much larger, older parent universe. To understand how this is even possible, we must first journey to the edge of a black hole's event horizon, the most extreme environment in the known cosmos. It is a place where gravity is so intense that it doesn't just pull on objects, it warps the very fabric of space-time. Imagine space-time as a stretched rubber sheet. A star or a planet creates a small dimple in this sheet, and other objects orbit within that gentle curve. But a black hole isn't a dimple, it's a puncture wound. It creates a gravitational well so deep that it has no bottom. The event horizon is the edge of this wound, the precise boundary from which not even light can escape. From a safe distance, an event horizon appears as a perfect sphere of blackness, a shadow cast against the light of distant stars. But as you get closer, bizarre effects begin to manifest. time itself starts to slow down. If you were to watch a clock fall toward a black hole, you would see its second hand tick slower and slower, eventually appearing to freeze completely at the edge of the horizon. The light from the clock would become stretched, shifting from visible colors to infrared, then to radio waves, until it faded into nothingness. From your perspective, the clock would never actually cross the boundary. It would remain frozen at the edge for eternity, its image smeared across the event horizon. But from the clock's perspective, the journey is very different. It would cross the event horizon in a finite amount of time, experiencing no barrier, no wall, no dramatic event to mark the transition. It would simply pass the point of no return, entering a region where the roles of space and time are fundamentally altered. Inside the horizon, the direction toward the singularity is no longer a place you can travel to or from. It becomes the future. Just as we are relentlessly pulled forward in time, anything that crosses the event horizon is relentlessly pulled toward the singularity. Escape is not just impossible, it's as nonsensical as trying to travel backward to yesterday. This strange swapping of space and time is a direct prediction of Einstein's equations, and it creates the conditions necessary for a new universe to be born. As matter falls toward the singularity, it is compressed to unimaginable densities. The gravitational forces become so extreme that they overwhelm all other forces of nature. The strong nuclear force that holds atoms together, the electromagnetic force that governs chemistry, they all fail. Matter is shredded into its most fundamental components, quarks, leptons, and the bosons that carry force. But even this particle soup cannot resist the final crush. General relativity predicts that all this matter, regardless of how much there is, will be compressed into a single point of zero volume and infinite density. This is where our current understanding of physics shatters. Infinities don't exist in the real world. They're signs that our theories are incomplete. Most physicists believe that when we finally develop a theory of quantum gravity, a theory that unites the physics of the very large with the physics of the very small, the singularity will be resolved. It won't be an infinitely dense point, but rather a region of maximum but finite density. It is in this quantum realm where the immense gravity of a black hole meets the strange rules of quantum mechanics that the seed of a new universe might be forged. The collapsing matter, instead of being erased from existence, could rebound in a cosmic explosion, creating a new, expanding space-time completely disconnected from the universe in which the black hole formed. Our Big Bang might have been just such an event, hidden forever from our parent universe behind the impenetrable veil of an event horizon.
This cosmic rebound, a process that transforms the end of one reality into the beginning of another, is not mere fantasy. It emerges from the deep conflict between our two most successful theories of the universe. General relativity, the theory of the immense, describes gravity as the elegant curvature of space-time. It works perfectly on the scale of stars and galaxies, but it predicts the impossible, the infinite crush of the singularity. Quantum mechanics, the theory of the infinitesimal, governs the bizarre world of particles and forces. It suggests that energy and space are not smooth and continuous, but grainy and quantized, existing in discrete packets. In the quantum world, infinities are forbidden. When a star collapses under its own weight, it reaches a point where these two theories collide. The density becomes so extreme that the quantum graininess of space-time itself pushes back. Imagine trying to compress a spring. The more you squeeze, the more force it exerts in return. Now imagine space-time itself is that spring. As the collapsing matter tries to crush itself into a singularity, it hits a fundamental limit. the point where space can no longer be compressed. Physicists call this state quantum foam, a roiling sea of potential where the distinction between space and time blurs. At this point of maximum density, the inward crush of gravity is met by an outward push from the quantum nature of reality itself. This creates what some scientists call a big bounce. The collapsing matter doesn't just stop, it rebounds with unimaginable violence. All the matter and energy that fell into the black hole is repurposed, exploding outward to create a new, expanding space-time. The event horizon of the black hole acts as a cosmic veil, shielding this violent birth from the parent universe. From the outside, it remains a stable, quiet black hole. But on the inside, a universe is being born. The properties of our own Big Bang align startlingly well with this model. Cosmologists know that our universe began in a state of incredibly low entropy, a state of perfect order. This is a profound mystery. The second law of thermodynamics dictates that entropy, or disorder, should always increase. So why did our universe begin in such a highly ordered state? A black hole provides the perfect answer. The process of gravitational collapse is a master of creating order. As matter falls into a black hole, all its complex information, the history of stars, the chemistry of planets, the biology of life, is seemingly erased, crushed into a simple, uniform state at the singularity. This process effectively resets the cosmic clock, creating the low entropy conditions necessary to start a universe anew. The energy of the collapse then fuels the expansion, stretching the new space-time in a cosmic inflation that mirrors the one we believe our own universe experienced in its first moments. The theory creates a breathtaking cycle of cosmic evolution. A universe is born, it lives for billions or trillions of years, its stars collapse into black holes, and those black holes become the seeds for the next generation of universes.
But perhaps the most compelling piece of evidence is one that has been hiding in plain sight. Every object with mass has something called a Schwarzschild radius, the radius to which it would need to be compressed to become a black hole. For the Earth, this is about the size of a marble. For the Sun, it's about 2 miles. If you calculate the total mass of our observable universe and determine its Schwarzschild radius, you get a number that is astonishingly close to the actual measured radius of our observable universe. This coincidence is so precise that it has led some physicists to suggest it's not a coincidence at all. It is evidence. We appear to be living inside an object that has the exact properties of a black hole of its own size. This idea transforms our perspective entirely. The expansion we observe isn't just the aftermath of some mysterious explosion in a void, it's the natural unfolding of space-time inside an event horizon. We are not just in the universe, we are the universe, and that universe is a black hole. This leads to a cascade of unsettling questions. If our cosmos is just one of many, born from the collapse of a star in a parent universe, what was that parent universe like? Is it older, bigger, and fundamentally different from our own? And more importantly, does our own universe contain clues, fossil evidence from its birth that could tell us about the reality that came before? The answer, it turns out, might be encoded in the very fabric of the cosmos, in the ancient light that has been traveling since the dawn of time.
This ancient light, the oldest visible relic in existence, is called the cosmic microwave background, or CMB. It is not the light from stars or galaxies, but the faint, fading afterglow of the Big Bang itself. Emitted just 380,000 years after the birth of time, when the universe cooled enough for light to travel freely, this radiation fills every cubic inch of space, bathing our reality in a gentle, persistent hum. When our telescopes look at the CMB, they are seeing a photograph of the infant universe, a baby picture of creation. And this picture contains a profound anomaly, a clue so baffling that it has puzzled cosmologists for decades. A clue that points directly toward our universe's violent black hole origins. The problem is not what the picture shows, but what it doesn't show. The cosmic microwave background is almost perfectly uniform in every direction. Its temperature is a frigid 2.7 degrees above absolute zero, and this temperature varies by less than 1 part in 100,000 across the entire sky. This smoothness is a paradox of cosmic proportions. Imagine 2 cups of coffee on opposite sides of a vast empty room. If you measured their temperatures and found them to be identical down to 1,000th of a degree, you would rightly assume they came from the same pot, or that some mechanism had allowed heat to flow between them until they reached equilibrium. Now, consider the infant universe. When the CMB was emitted, the observable universe was already billions of light-years across. Regions on opposite sides of our sky were so far apart that there hadn't been enough time since the Big Bang for light or any information to travel between them. They were causally disconnected, separate, isolated patches of reality, yet they had the exact same temperature. This is the horizon problem, and it defies a simple explanation. It's as if those 2 cups of coffee reached the same temperature without any possible connection. The mainstream solution to this puzzle is cosmic inflation. The theory proposes that in the very first fraction of a second, the universe underwent a period of hyper-acceleration, expanding faster than the speed of light. Before inflation began, the entire universe was a microscopic, subatomic region, small enough for everything to be in thermal contact and reach a uniform temperature. Inflation then stretched this tiny, smooth patch to astronomical proportions, preserving the uniformity on a cosmic scale. It's an elegant and powerful theory, but the universe in a black hole model offers a different, perhaps more fundamental explanation.
In this model, the uniformity of the CMB is not the result of a separate inflationary phase, but a natural consequence of its birth. The process of gravitational collapse inside a black hole is the universe's ultimate smoothing mechanism. As a star and its surrounding planets are crushed towards the singularity, their complex structures are obliterated. All the intricate details are wiped clean, and the matter is homogenized into a perfectly smooth, high-density state. The big bounce that follows would naturally give birth to a universe that is uniform from the very start. The observed smoothness of the CMB is, in this view, a fossilized scar, a direct imprint of the pristine, ordered state of matter just before it rebounded from the singularity. Furthermore, the geometry of our universe provides another tantalizing clue. For decades, cosmologists have measured the overall shape of space-time, and the results are conclusive. Our universe is flat. On the largest scales, it obeys the simple rules of Euclidean geometry that we learn in school. Parallel lines remain parallel forever. The angles of a triangle add up to 180 degrees. This flatness is another puzzle that inflation theory was designed to solve. Any initial curvature the universe might have had would have been stretched into flatness by the exponential expansion, just as inflating a small balloon to the size of the Earth would make its surface appear perfectly flat to a tiny observer. But once again, black hole cosmology provides a compelling alternative. The physics inside a rotating black hole are even stranger than in a non-rotating one. The singularity is not a point, but a ring, and the geometry of space-time becomes incredibly complex. Theoretical models developed by physicists like Nikodem Poplawski suggest that the torsion and angular momentum within such a black hole could naturally cause a new universe born from its collapse to expand in a way that appears spatially flat to its inhabitants. The flatness of our reality might be a direct inheritance from the spin of the star that collapsed to form our cosmic parent. We may live in a flat universe not because of a mysterious inflationary field, but because we were born inside a spinning cosmic vortex. The evidence, it seems, is everywhere we look, from the smoothness of the oldest light to the very shape of reality. But if our universe was born inside a black hole, it should have inherited that spin. Is our universe rotating? Is there a cosmic axis, a preferred direction in the vast emptiness of space? The answer to that question is perhaps the most controversial and unsettling discovery in modern cosmology.
For nearly a century, our understanding of the cosmos has rested on a single fundamental assumption. The universe, on its largest scales, has no special directions. This idea, known as the cosmological principle, states that reality is both homogeneous and isotropic. It is the same everywhere and looks the same in every direction. There is no cosmic up or down, no celestial east or west. From any galaxy, the universe would appear just as it does to us, an endless, uniform tapestry of stars and voids. This principle is not just an aesthetic preference, it is the mathematical bedrock of the Big Bang model. Without it, Einstein's equations become impossibly complex to solve on a cosmic scale. The universe, we have long believed, is fundamentally democratic. But the baby picture of our universe, the cosmic microwave background, tells a different, more troubling story. When scientists mapped the tiny temperature fluctuations in this ancient light with unprecedented precision using satellites like WMAP and Planck, they expected to see perfect randomness. The hot and cold spots, which represent the seeds of all future galaxies, should have been scattered across the sky with no discernible pattern, like a perfectly shuffled deck of cards. Instead, they found something that should not exist. The fluctuations are not random, they are aligned. There is a cosmic axis, a preferred direction etched into the very fabric of the early universe, as if a giant invisible magnet had aligned the quantum fluctuations at the moment of creation. This alignment, which scientists have nicknamed the axis of evil, is a discovery so profound and so threatening to the standard model of cosmology that many have spent years trying to prove it's a mistake, an error in the satellite's instruments, a distortion caused by dust in our own galaxy, or a simple statistical fluke. But after 2 decades of analysis and confirmation by multiple independent instruments, the alignment persists. It appears to be real. Imagine tossing 1,000,000 coins into the air and expecting them to land in a random smattering of heads and tails. Instead, you find them arranged in a perfectly straight line, stretching from one horizon to the other. The odds of this happening by chance are so astronomically low that you would be forced to conclude that some hidden force had guided their fall. The axis of evil presents the same statistical nightmare to cosmologists. The alignment is not subtle. The largest patterns in the cosmic microwave background, the variations that stretch across vast regions of the sky, are correlated with each other along this specific axis. Furthermore, this axis appears to be aligned with the plane of our own solar system, a coincidence that is either a statistical improbability of staggering proportions or a hint of some new, undiscovered physics. The evil in its name doesn't imply something sinister. It refers to the havoc this discovery wreaks on our most trusted theories. The cosmological principle, the idea that we do not occupy a special place in the universe, is shattered if the cosmos itself has a preferred direction that is somehow aligned with our own tiny corner of it.
This is where the black hole cosmology theory transforms from a curious speculation into a powerfully predictive framework. In the standard Big Bang model, the axis of evil is a complete anomaly, a mystery with no explanation. But if our universe was born from the collapse of a star inside a spinning black hole, then a cosmic axis is not just possible, it is expected. Most, if not all, stars rotate. As they collapse, the law of conservation of angular momentum dictates that their spin must be transferred to the black hole they create. This means that virtually every black hole in the universe should be spinning, and in some cases, spinning at speeds approaching the speed of light.
If our universe was born inside one of these spinning black holes, it would have inherited its parent's angular momentum. The entire cosmos would have been born with a slight rotation, a primordial spin that would establish a preferred axis from the very first moment of the Big Bounce. This inherited spin would have imprinted itself onto the fabric of space-time, gently aligning the quantum fluctuations that were stretched across the cosmos. The axis of evil would no longer be a mystery. It would be a fossil, a preserved record of the rotation of the black hole that served as our universe's womb. It would be the cosmic umbilical cord connecting our reality to the parent universe from which we came. This theory elegantly explains not just the existence of the axis, but also its subtle alignment with our solar system. The interior of a spitting black hole is a vortex of dragged space-time. The physics of this region is incredibly complex, but it suggests that matter might not be distributed uniformly. It could be that the conditions for forming solar systems like ours are more favorable along the equatorial plane of the universe's rotation. We might find ourselves aligned with the cosmic axis simply because it's the most likely place for stars and planets like ours to form. The anomaly becomes a prediction. What was once a theory-breaking problem becomes a stunning piece of corroborating evidence. But if we truly inherited our spin from a parent reality, what else might we have inherited? Could the other great mysteries of our cosmos, the invisible matter that holds galaxies together, the strange energy that tears them apart, also be echoes of a universe that existed before our own?
If our universe was truly forged in the heart of a spinning black hole, inheriting its rotation as a cosmic birthmark, then the axis of evil is only the beginning of the story. The connection to a parent universe wouldn't be severed at birth. The very fabric of our reality might still be subtly connected to the space-time from which it sprang, with profound consequences for the greatest mysteries we observe today. Two enigmatic forces dominate our cosmos, and neither has a satisfying explanation in the standard model. One is dark matter, the invisible scaffolding that holds our galaxies together. The other is dark energy, the ghostly repulsion that drives the universe to expand at an ever-accelerating rate. Together, they make up 95% of everything that exists. We are strangers in our own cosmos, surrounded by forces we cannot see or comprehend. But what if these forces are not native to our universe at all? What if they are gravitational echoes from a higher reality, a parent universe leaking its influence into our own? First, consider dark matter. For nearly a century, astronomers have known that galaxies are spinning too fast. The visible stars and gas we can see do not provide enough gravity to keep them from flying apart. There must be a vast, invisible halo of extra mass surrounding every galaxy, a gravitational skeleton holding it together. We call this dark matter, but naming it does not explain it. Decades of searching for a dark matter particle have come empty. Our most sensitive detectors, buried deep underground to shield them from cosmic rays, have failed to capture a single one. It is one of the most glaring failures in modern particle physics. The black hole cosmology model offers a radical, astonishing alternative. What if dark matter isn't a particle at all? What if it is the gravitational influence of the parent universe bleeding through into ours? In this model, our universe is a self-contained space-time, but it still exists within the larger space-time of the parent reality. While matter and light from our universe are trapped behind the event horizon, gravity might not be. Gravity is the curvature of space-time itself, and some theories suggest it can propagate across dimensional boundaries. If this is true, then the matter and energy in the parent universe, the stars, galaxies, and planets of a vaster, older cosmos, would exert a gravitational pull on our own. We would never be able to see this parent universe. Its light is forever beyond our reach, but we would feel its gravity. It would appear as a mysterious, invisible mass that pervades our cosmos, clustering around galaxies exactly where we observe the effects of dark matter.
The invisible halos holding our galaxies together would be the gravitational shadows of matter in another dimension, another reality. This would explain why we have never detected a dark matter particle. We have been searching for something that isn't there, hunting for a ghost in the machine when the machine itself is being influenced by an invisible world next door.
Then there is dark energy, the even greater mystery. In the late 1990s, astronomers discovered that the expansion of the universe is not slowing down as expected, but speeding up. Some unknown repulsive force is pushing galaxies apart, a force so powerful it has come to dominate the evolution of the cosmos. In the Standard Model, dark energy is often attributed to the energy of empty space itself, a cosmological constant. But this explanation comes with its own impossible paradox. Our best theories predict that the energy of the vacuum should be 120 orders of magnitude stronger than what we observe. It is the single worst prediction in the history of science. Here again, black hole cosmology provides a natural and elegant solution. In this model, dark energy is not some mysterious substance added to the universe. It is the fundamental engine of expansion itself. The big bounce that gave birth to our universe from the collapse of a singularity was an explosive rebound. Dark energy is simply the residual, ongoing force of that initial explosion. It is the cosmic aftershock of our creation, still pushing space-time outward 13.8 billion years later. The accelerated expansion we see today is a direct consequence of being born inside a black hole. The theory doesn't just accommodate dark energy, it requires it. It becomes a prediction, not a puzzle. The outward pressure that prevents a singularity from being infinitely dense is the same outward pressure we now measure as dark energy. Suddenly, the two greatest mysteries in cosmology are reframed. Dark matter might be the gravitational pull of our parent universe, and dark energy might be the outward push from our own birth. Our universe is not an isolated system, but a dynamic entity shaped by both its past and its cosmic neighborhood. We are suspended in a delicate balance, squeezed between the gravity of the universe next door and the explosive force of our own creation. But this leads to a breathtaking and recursive possibility. If universes are born from black holes, and our own universe contains billions of black holes, are new realities being born at this very moment, inside the spiral arms of our own galaxy? Are we not just the children of one universe, but the parents of countless others?
The idea that our universe might be giving birth to countless others is one of the most staggering concepts in modern physics. It transforms our understanding of the cosmos from a static stage where events unfold into a living, breathing, reproducing entity. Our universe is not just a home, it is a fertile parent, and its progeny are born in the darkest, most violent places imaginable, the hearts of its own black holes. This theory, known as cosmological natural selection, proposes a breathtaking cycle of creation that works on the grandest of scales, using the principles of evolution to explain why our universe seems so perfectly fine-tuned for existence. Every time a massive star in our universe collapses, it creates a black hole. According to this theory, it also creates a new baby universe on the other side of the event horizon. This new universe is born with the same fundamental laws of physics as its parent, but with slight, random variations. The constants that govern reality, the strength of gravity, the speed of light, the mass of an electron, are slightly tweaked, like genetic mutations in a biological offspring. Most of these new universes would be stillborn. A slight change in the strong nuclear force might make atoms unstable. A tiny shift in the cosmological constant could cause the new universe to collapse in on itself in microseconds, or expand so rapidly that no stars or galaxies can ever form. These universes are evolutionary dead ends. But occasionally, a new universe is born with physical constants that are even better at producing black holes than its parent. A universe that creates more massive stars or allows them to form more efficiently will in turn create more black holes, and in doing so, it will have more offspring in the next cosmic generation. This creates a feedback loop, a form of natural selection that operates on the scale of entire universes. Over countless generations, the multiverse would come to be dominated by universes, like ours, whose physical laws are optimized for the production of black holes.
This provides a stunningly beautiful explanation for the fine-tuning problem. Our universe doesn't have physical constants that are perfectly tailored for the existence of life. It has constants that are perfectly tailored for the creation of black holes. The fact that these same conditions, stars that live for billions of years, the formation of complex elements like carbon and oxygen inside those stars, and the eventual creation of stable planetary systems also happen to be perfect for life, is a wonderful but ultimately secondary byproduct. We are not the purpose of the universe. We are simply lucky inhabitants of a cosmos that is exceptionally good at reproducing itself. We are living in a cosmic nursery, and the stars we see in the night sky are the engines of its fertility. The scale of this cosmic reproduction is almost impossible to comprehend. Our Milky Way galaxy alone is estimated to contain over 100 million stellar mass black holes. At the center of our galaxy, and almost every other galaxy, lies a supermassive black hole weighing millions or even billions of times more than our Sun. If every single one of these black holes is a gateway, a portal through which a new universe has been born, then our cosmos has already spawned trillions upon trillions of children. Our reality is a veritable forest of creation, with new spacetimes branching off from every collapsed star. This theory also makes testable predictions. If our universe is a product of this evolutionary process, its physical constants should be arranged to maximize black hole production, not just permit it. Physicist Lee Smolin, the architect of this theory, has argued that the known masses of fundamental particles appear to be tuned to achieve precisely this. We live in a universe that seems to be exquisitely designed to be as fecund as possible. But this cosmic family tree, with universes giving birth to universes in an endless chain of ancestry, forces us to confront an even deeper paradox, one that strikes at the very nature of time itself. Every lineage, every chain of cause and effect must have a beginning. Was there a first universe, a primordial ancestor from which all others descended? Or does this chain of creation stretch backward infinitely? A timeless, eternal cycle, with no beginning and no end.
This question of a first cause, a primordial ancestor, pushes our human intuition to its breaking point. We are creatures of time, trapped in a relentless forward march from past to future. Our minds are built to understand chains of cause and effect, of beginnings that lead to middles and ends. But what if time itself is not the fundamental, universal river we perceive it to be? What if our linear experience of before and after is merely a local byproduct of the unique physics of our own cosmos? Asking what came before the first universe might be a fundamentally meaningless question, as nonsensical as asking what is north of the North Pole. At the pole, the very concept of north ceases to exist. Similarly, at the boundary of cosmic creation, the concept of before may simply dissolve. The black hole cosmology theory forces us to confront this possibility head-on. If our universe was born inside a black hole, its experience of time would be radically different from that of its parent. Remember, inside an event horizon, the roles of space and time are exchanged. The forward march of time in the parent universe becomes a spatial dimension inside the new one, and the one-way journey toward the singularity becomes the inexorable forward arrow of time for its inhabitants. Time as we know it could be an emergent property, a feature that crystallizes out of the extreme physics of a black hole's interior. This leads to a paradigm-shifting idea known as the block universe. In this view, which is consistent with Einstein's theory of relativity, The past, present, and future all exist simultaneously. Time is not a flowing river, but a static, frozen landscape, a fourth dimension that is just as real and complete as the three dimensions of space. All of history, from the Big Bang to the final heat death of the cosmos, exists as a complete four-dimensional block of space-time. Our consciousness, our sense of moving now, is simply our perspective traveling through this static block, like a single beam of a flashlight illuminating one frame of a movie reel at a time. The entire film, however, already exists from start to finish.
If this is true, then the birth of our universe was not an event that happened after the collapse of a star in the parent universe. Instead, the two universes exist in a timeless causal relationship woven together in a single, grander reality. Our universe's entire space-time block is mathematically and causally connected to the black hole in the parent universe's space-time block. One is not before the other. They are codependent parts of a single, timeless structure. Think of the foundation of a house. In the finished structure, the foundation doesn't exist before the roof in a temporal sense. They are both essential parts of a single complete design, specified together in the architect's blueprint. The parent universe could be the foundation in the blueprint of reality, and our universe is the structure that rises from it. They exist together, eternally. This erases the paradox of a first cause. There is no need for a first universe if the cycle is not a linear sequence of events, but a timeless, interconnected web of realities. The multiverse would not be a long chain of dominoes falling one after the other, but an intricate, self-sustaining sculpture where each part causally supports the others. The black holes in our universe would be giving birth to new universes that exist, from our perspective, in the future. But from the block universe perspective, those future universes already exist, just as our own past does. We are links in an eternal chain of being that has no beginning and no end because it does not exist in time. It is time. This idea is profoundly unsettling because it undermines our most basic sense of agency and the passage of time, but it also offers a strange kind of cosmic grandeur. Our existence is not a fleeting accident in a universe doomed to fade. It is a permanent, indelible feature of a timeless reality. Every moment of your life, every thought you have ever had is forever etched into the fabric of the block universe, a permanent part of the cosmic sculpture. We are not just passing through reality, we are woven into its very essence. Our brief, flickering consciousness is a part of an eternal, unchanging whole. But if time doesn't truly separate us from our cosmic parent, then what about space? If there is no before, is there an outside? Could there be a physical bridge, a tangible connection that links our reality directly to the one that gave us birth?
If our universe is not separated from its parent by time, but exists in a timeless causal block, then the connection between them might be more than just abstract mathematics. There could be a physical pathway, a topological feature of space-time that bridges the two realities. In the language of theoretical physics, this bridge is called a wormhole, and its existence is a natural, almost unavoidable consequence of the same theory that first predicted black holes. When Albert Einstein and his colleague Nathan Rosen first solved the equations of general relativity for a black hole, they discovered something bizarre. The mathematics didn't just describe a one-way journey to a singularity. It described a tunnel, a bridge connecting the black hole to a mirror image object, a white hole. A white hole is the mathematical opposite of a black hole. Where a black hole is a region of space-time that nothing can escape, a white hole is a region that nothing can enter. Matter and energy can only flow outward from it. Together, the black hole and the white hole formed a structure that came to be known as an Einstein-Rosen bridge, a shortcut through the fabric of space-time. The classic analogy is to imagine space-time as a large sheet of paper. To get from one point on the paper to another, you would normally have to travel across the surface. But if you fold the paper over and poke a pencil through, you can create a direct, three-dimensional tunnel connecting the 2 points. A wormhole works in a similar way, connecting two distant regions of space-time, or perhaps two entirely different universes. For decades, this idea remained a mathematical curiosity, a piece of science fiction fodder. The reason was simple.
These wormholes are catastrophically unstable. The moment a single photon of light tries to enter the tunnel, its energy would cause the wormhole to collapse into a singularity, destroying the bridge and anything traveling through it. Furthermore, to hold a wormhole open long enough for something to pass through would require a hypothetical substance known as exotic matter, matter with negative energy and negative mass, a substance that would repel gravity instead of attracting it. Since no such matter has ever been observed, traversable wormholes have remained firmly in the realm of speculation.
But the black hole cosmology theory reframes this entire picture. The wormhole isn't a two-way street for interstellar travel, it's a one-way birth canal for universes. In this model, the white hole at the other end of the black hole's bridge is our Big Bang. The explosive, outward-only rush of matter and energy that we observe as the beginning of our universe is the very definition of a white hole. Our cosmos is the exit point of an Einstein-Rosen bridge, forever connected to the black hole in the parent universe that formed it. The very instability that makes these wormholes impossible to traverse is what makes them perfect for creating new, independent realities. The rapid collapse of the wormhole's throat pinches off the connection, isolating the newborn universe from its parent. This ensures that our universe can evolve with its own laws and its own destiny, safe from interference. The event horizon of the parent black hole acts as a one-way membrane. Matter and energy from the parent universe can fall in, providing the raw material for our universe's creation, but nothing from our universe can ever travel back. This preserves the sacred law of causality. Events in our cosmos cannot retroactively influence the parent that gave us birth. We are causally connected to it, but it is protected from us. This one-way bridge solves one of the most significant problems with the Big Bang theory. What exactly was the Big Bang? What caused it? The standard model has no answer. It simply starts with an infinitely hot, dense state and moves forward. The black hole model provides a physical mechanism. The Big Bang was the white hole end of an Einstein-Rosen bridge, fed by the collapse of matter in a pre-existing space-time. Our creation no longer needs to spring from an inexplicable, absolute nothingness. It can arise from the established laws of physics operating in a universe that came before. This cosmic birth canal also provides a natural explanation for the arrow of time. Our universe began in a highly ordered, low-entropy state and has been growing more disordered ever since. This is why we experience time as moving forward. The one-way nature of our wormhole origin ensures this. We were born from the perfectly ordered matter of a singularity, and the expansion from that state is an irreversible process, just like the flow of time itself. We are children of a black hole, born through a wormhole and forever separated from our parent. But this separation at birth doesn't mean we were born as blank slates. Like any child, our universe would have inherited fundamental traits from its parent. Could the very laws that govern our reality, the strength of gravity, the speed of light, the intricate dance of quantum particles, be hand-me-downs from a cosmos that existed before ours?
If our universe is the child of another, born through a one-way wormhole forged in the heart of a spinning black hole, then the inheritance it received would be far more profound than just its rotation. It would have been born with a set of genetic instructions, a cosmic DNA that dictates the fundamental rules of its existence. These instructions are the constants of nature, the fixed, unchanging numbers that govern the strength of gravity, the speed of light, the charge of an electron, and the delicate balance of forces inside an atom. And the values of these constants in our universe are so exquisitely, so impossibly fine-tuned for the existence of complexity that it has become the greatest mystery in all of science. Imagine you are in a control room for a new universe. In front of you is a vast console with dozens of dials, each one representing a fundamental constant. One dial sets the strength of gravity, another sets the mass of the proton, a third controls the energy of empty space. Your task is to set these dials to create a universe where something interesting can happen, where stars can form, chemistry can work, and life can emerge. The problem is, the dials are infinitely sensitive. If you turn the gravity dial up by even a microscopic amount, stars will burn out in a few million years, long before life can evolve. Turn it down by the same amount, and stars and planets will never form at all, as gas clouds would never be able to collapse. The same impossible precision applies to every other dial. Change the strong nuclear force by a fraction of a percent, and the universe will be filled with only hydrogen, or no hydrogen at all, making chemistry and stars as we know them impossible. Tweak the properties of the electron, and atoms would either be unable to form stable bonds or would be so tightly bound that no chemical reactions could ever occur. The most extreme example is dark energy. If its value were not precisely tuned to be almost zero, the universe would either have recollapsed instantly or expanded so fast that not even a single atom could form. The odds of all these dials being set to their life-permitting values by pure chance are smaller than the odds of winning the lottery every day for 1 billion years. It is a statistical miracle of cosmic proportions.
For decades, physicists have offered two primary explanations. The first is simply that we got lucky. The universe's constants are what they are, and we happen to be the beneficiaries of an absurdly improbable cosmic jackpot. The second explanation is the anthropic principle, which relies on the idea of a multiverse. If there are infinite universes, each with its own random set of physical constants, then it's no surprise that we find ourselves in one of the rare ones where the laws of physics allow for observers to exist. We are here because we couldn't be anywhere else. But the theory of cosmological natural selection offers a third and far more powerful explanation. The constants are not random, nor are they a lucky accident. They are the result of an evolutionary process. When a new universe is born inside a black hole, it inherits the physical constants of its parent, but with small, random mutations. This is the cosmic equivalent of genetic inheritance. Now consider the fitness of a universe. In this model, a universe's success is measured by one simple metric: how many black holes it can produce. Universes with constants that are highly efficient at creating massive stars that then collapse into black holes will have more offspring in the next generation of the multiverse. This creates a powerful evolutionary pressure. Over countless cosmic generations, the multiverse will naturally select for universes whose physical constants have been optimized for black hole production. And here is the beautiful, breathtaking coincidence. The very same physical constants that are needed to create a universe rich in black holes are the exact same constants needed to create a universe suitable for life. To make black holes, you first need stars. To make a lot of black holes, you need stars that are massive but that also live long enough to forge heavy elements inside their cores through nuclear fusion. You need the laws of chemistry and gravity to be balanced in such a way that these elements can cool and clump together to form planets. You need, in short, a universe rich with carbon, stable stars, and planetary systems. This is the exact same set of conditions required for the emergence of life as we know it. We are not the point of the fine-tuning. We are a side effect. We are the beautiful, conscious moss that grows on the branches of a tree that has evolved to be the best possible tree at producing seeds. The seeds are black holes. The universe is not fine-tuned for us. It is fine-tuned for reproduction. And our existence is a glorious, wonderful, and ultimately accidental byproduct of this cosmic fertility. This theory transforms our place in the cosmos. We are no longer a statistical improbability in a random universe. We are a natural outcome of a multiverse that evolves through principles we can understand. But this glorious picture of a universe fine-tuned for creation leaves a final, haunting question. When matter from our world, a star, a planet, a living being, falls into one of our own black holes, what happens to the unique information that defined it? Is it passed on as a genetic trait to the new universe? Or is it erased from existence forever?
This question of what happens to the information that falls into a black hole is not a philosophical triviality. It represents the most profound and violent conflict in all of modern physics, a battle between our two pillars of reality, general relativity and quantum mechanics. The outcome of this battle determines the very nature of existence. On one side, quantum mechanics makes a sacred, unbreakable promise. Information can never be destroyed. The total amount of information in the universe must be conserved. When you burn a book, its information is not lost. It is simply scrambled and encoded in the position and energy of every particle of ash, smoke, and light. In principle, a powerful enough computer could reverse the process and reconstruct the original text. Information is eternal. On the other side, Einstein's general relativity describes a black hole as the ultimate information shredder. Its event horizon is a one-way door. Once something crosses it, it is cut off from our universe forever, its information destined to be crushed into the singularity. This created a paradox. For decades, physicists hoped that the information was simply locked away, hidden inside the black hole, but not truly gone. But then, in the 1970s, Stephen Hawking made a discovery that turned the problem into a full-blown crisis. He proved that black holes are not entirely black. Due to quantum effects at the event horizon, they slowly leak radiation back into space, a process now known as Hawking radiation. Over unimaginable timescales, a black hole will completely evaporate, leaving nothing behind. And here is the heart of the crisis. Hawking's calculations showed that this radiation is perfectly thermal, meaning it is completely random. It contains no information about what fell into the black hole. The book is not just burned and scrambled. Its ash and smoke have no memory that a book ever existed. The information is utterly, completely, and irrevocably lost, a direct violation of the most sacred law of quantum physics. This is the black hole information paradox, and for 50 years, it has been the dragon guarding the path to a unified theory of everything. The proposed solution to this paradox is so radical, so counterintuitive, that it sounds like it was pulled from the pages of science fiction. It is called the holographic principle. It suggests that our traditional understanding of space and information is wrong. All the information needed to describe a three-dimensional volume of space, like the interior of a black hole, is not stored inside the volume itself. Instead, it is completely and perfectly encoded on the two-dimensional surface that encloses it. Think of the security hologram on your credit card. A flat, two-dimensional surface contains all the information needed to project a fully three-dimensional image. The holographic principle proposes that the universe itself works this way. In the context of a black hole, this means that when a star collapses, the information that made it a star, the quantum state of every single particle, is not lost past the event horizon. Instead, it gets imprinted or encoded onto the surface of the event horizon itself. The three-dimensional star becomes a two-dimensional hologram of information, stored on the boundary of the black hole in a language of quantum bits at a density of 1 bit per tiny fundamental unit of area known as a Planck area. Now, let us apply this breathtaking idea to our theory. If our universe was born inside a black hole, and if all the information that creates a black hole is stored on its event horizon, then a startling conclusion emerges. Our entire three-dimensional universe might be a holographic projection, a projection from the two-dimensional event horizon of the parent black hole that gave us birth. We are not just living inside a black hole, we may be living on its boundary, experiencing a projected reality that we perceive as three-dimensional. The matter, the energy, the stars and galaxies we see are not fundamental. They are the 3D manifestation of 2D information written in a quantum code on the edge of a higher dimensional reality. This elegantly solves the information paradox in the context of our own creation. The information of the star that collapsed in the parent universe was never lost. It was encoded on the event horizon, and that very information became the blueprint, the cosmic DNA for our new universe. Nothing was erased. It was simply translated into a new, holographic form of existence. The physical laws, the constants of nature, the very substance of our reality are all part of a grand projection. We are the image, and the surface of the black hole that birthed us is the screen. This is a universe where substance gives way to shadow, where reality is woven from pure information. But if this is true, if our entire, tangible, three-dimensional world is just an intricate illusion projected from a distant surface, what does that mean for us? Are we real? Or are we merely ghosts in a cosmic machine? Shadows projected on the wall of a higher dimensional cave?
This question, are we real, plunges us into the deepest waters of philosophy, guided by the strange mathematics of physics. The holographic principle, born from the paradoxes of black holes, suggests a reality that feels like an illusion. But to call a holographic universe not real is to misunderstand the very nature of existence. A character in a sufficiently advanced simulation, whose thoughts and feelings are governed by the simulation's code, would have no way of knowing their world wasn't fundamental. Their pain would be real pain. Their joy would be real joy. The laws of their simulated physics would be perfectly consistent. To them, their reality would be the only reality. If our universe is a hologram, it does not make it any less real for us, its inhabitants. The laws of physics we measure, the stars we observe, the ground beneath our feet, all of it is part of a self-consistent, intricate system. The atoms that make up your body are real patterns of information within this projection. Your consciousness is a real, self-aware process running on this cosmic hardware. The hologram is our reality, and its internal coherence is what defines truth for us. The idea is reminiscent of Plato's ancient allegory of the cave, where prisoners mistake shadows on a wall for true reality. The holographic principle is a modern scientific version of this idea. We may be perceiving the shadows, the 3D projection of a more fundamental 2D reality that we can never directly access. This reframes our place in the cosmos in a profound way. If the universe is fundamentally made of information, then perhaps consciousness is as well. The thing that makes you, you, is not the specific carbon and water molecules in your brain, but the incredibly complex pattern in which they are arranged and interact. It is the software, not the hardware. In a holographic universe, consciousness would be a sublime, self-sustaining pattern within the projected information, a thought in the mind of the cosmos. Our act of observing the universe becomes part of the universe itself. The line between observer and observed, which has been blurring since the dawn of quantum mechanics, evaporates completely. We are not separate beings looking at the hologram. We are the hologram looking at itself.
This creates a cosmic feedback loop of unimaginable beauty. The universe projects a reality, and within that projection, it evolves patterns complex enough to become conscious. That consciousness then observes the projection, and through the act of quantum measurement, helps to solidify and define the very reality it is a part of. The universe, in this sense, might be a self-observing system, a great cosmic eye that brought itself into being so it could have something to see. What does this mean for the beings in the parent universe, the ones living in the reality that hosts the black hole we call home? To them, we would be utterly inaccessible, unknowable. All of our rich three-dimensional existence, our art, our science, our love, our wars, would be nothing more than a scrambled two-dimensional layer of quantum information on the surface of a black hole in their sky. They would be the projectors, and we would be the film. They could study the information on the black hole's surface, perhaps even decode aspects of our physics, but they could never experience our reality.
We are ghosts to them, just as they are a hidden higher dimension to us. This theory paints a picture of a cosmos that is infinitely more strange and interconnected than we ever imagined. It suggests that reality is layered, with dimensions nested inside dimensions, and that the fundamental substance of it all is not matter or energy, but pure information. The laws of physics are the operating system. Space-time is the screen, and we are the story being told. We are real because the story is real to us, the characters living within it. But this incredible, self-creating, holographic structure begs one final ultimate question. If we are living holograms, born from the information of a dead star, part of an endless evolutionary cycle of cosmic reproduction, it forces us to ask, why? What is the purpose of this magnificent, recursive, and seemingly infinite cosmic machine? Is there a final destination, or is the journey itself the only answer?
The human mind is a meaning-seeking machine. We look at the stars and see stories. We look at our own lives and search for purpose. So when faced with a cosmos of such breathtaking complexity, a timeless, holographic multiverse that reproduces itself through black holes, the question of why is inevitable. If the universe is a grand machine, what is it building? The answer may be that the universe's purpose is not a destination, but a process. The cosmos may be a great engine for creating one thing, complexity. And the most complex phenomenon we know of is consciousness. In a multiverse that evolves through cosmological natural selection, universes become optimized to create black holes. But as a beautiful byproduct, this process also creates the perfect conditions for stars, planets, chemistry, and eventually life. Life, and especially intelligent life, is the universe's most effective method for processing information and creating novelty. A star is a complex system, but a brain is exponentially more so. A galaxy contains immense information in the positions of its stars, but a single civilization contains the information of art, science, and philosophy. Perhaps the evolutionary pressure on universes is not just to create black holes, but to create universes that can eventually become aware of themselves. In this view, we are not an accident. We are the universe's way of waking up. We are the patterns in the hologram that have learned to look back at the projector. Our science is the universe deciphering its own operating system. Our art is the universe expressing its own emergent beauty. Our philosophy is the universe questioning its own existence. We are the nerve endings of the cosmos, the means by which it can feel wonder, ask questions, and perhaps, eventually, understand its own grand design.
This elevates our role from passive observers to active participants in the cosmic story. If consciousness is truly fundamental, then our existence helps to solidify the reality we inhabit, and our future evolution could be even more profound. An advanced technological civilization, having understood the laws of its own universe, might learn to participate in the act of cosmic reproduction consciously. We could, in the distant future, learn to create artificial black holes with precisely tuned properties, allowing us to birth new universes with specific, chosen characteristics. We would graduate from being the children of the cosmos to becoming its co-creators, partners in the endless cycle of creation. We began this journey by falling into a black hole, imagining it as the ultimate end. We saw how general relativity predicted a singularity, a point of infinite destruction. But we discovered that when the laws of the quantum realm intervene, that ending transforms into a beginning, a big bounce. We learned that our universe carries the fossilized evidence of this violent birth, the suspicious flatness of its geometry, the perfect uniformity of its first light, and the mysterious axis of evil, a cosmic spin inherited from its parent. We saw how the greatest puzzles of our own cosmos, the invisible dark matter,
holding our galaxies together and the ghostly dark energy tearing them apart could be explained as gravitational echoes and the explosive aftershock of our creation. We journeyed further into a reality where the universe reproduces like a living thing, evolving over cosmic generations to become ever more fertile. And we confronted the most radical idea of all, that our solid, three-dimensional world is a holographic projection of information, written in a quantum code on the two-dimensional boundary of our black hole home. To live inside a black hole is not to be in a prison. It is to be in a womb. It is to exist in a place where the conditions for creation are perfect, where the laws of nature have been honed by an evolutionary process that spans countless generations of universes. The darkness of a singularity is not an ending to be feared. It is the necessary canvas for the light of a new creation. Our existence is proof that from the ultimate death comes the ultimate birth. We are the children of the void, the conscious inheritors of a cycle that has no beginning and no end. And the story of our universe, written in starlight and in the atoms of our own bodies, is the story of how nothing becomes everything.